Hello everyone, this is Professor DePolo. Welcome you back to Psych 220 Behavioral Statistics, and I'm going to walk you through an example of ANOVA. So remember, ANOVA is when you have more than two groups. So you have three or more groups and you want to test if the groups are the same, which is the null hypothesis, or the groups are not the same, not all the same, which is the alternative. And when you reject the null, and you say the groups are not all the same, then you need to do post hoc tests to determine which groups are different from which other group. Now, in this problem here, which I set up for you, we're looking at back pain. So the following study is going to look at the effects of ibuprofen on treating back pain. Participants were randomly assigned to either receive a placebo, 200 milligrams ibuprofen, or 400 milligrams ibuprofen, and then they rated their back pain after taking the treatment on a scale of 1 to 10, with 10 meaning maximum pain. So to set this problem up, I copied down the three columns: the placebo column, which I'm calling X1, the 200 milligram column, right the middle column, which I'm calling X2, and the third 400 milligram column, which I'm calling X3. And I'm just copying down the data here. And then what I want to do is I want to make a squared column, x1 squared, x2 squared, and x3 squared, where I'm squaring all this data. This is how you set up the problem basically. So I'm starting out with this. I'm squaring all these values, and this is pretty basic. I don't even need a calculator for this. And now I have to add the totals out, which, you know, you want to be careful, so I would say use a calculator to double check. So I'm going to add all 6 of these columns. Now, the sum of these regular columns here are going to be called T. So this is going to be T1. This one is going to be T2. T being treatment totals, right? So T is treatment total. T3. So I'm just going to sum up all these columns, and then I'm going to sum up the x squared columns as well, because I'm going to need that also later on in the problem. So I'm going to break open R for that. And so let's do sum of placebo. Plant growth. So that gives me 45. That looks kind of sloppy, so let me fix that. So that's 45. And then I want sum of the 200 group. That gives me 25. And then I want the sum of the 400 group, which is going to give me 10. So those are my treatment total 1, treatment total 2, treatment total 3. Now for the x squared columns, sum these up. I don't need to label these because I'm just going to add them later together. So sum all these columns up. It's going to give me my total x squared for everything. So once again, we're going to do sum of placebo squared. That gives me 407. Let's do the sum of these other ones here. Sum of 200. Got to spell it right. That gives me 127. And let's do the x3 values, which is 400 squared. That gives me 22. Okay, let's move it a little bit to make more room here. So let me move this. So now I'm going to find a treatment total, which is called G, the grand total. That's equal to T1 plus T2 plus T3. So that's 45 plus 25 plus 10. 45 and 25 is 70, and 10, that's 80. So the grand total is 80. And I also needed x squared, a sum of x squared. So summing up all the x squared values, well, that's simply these other columns. So column 2, column 4, and column 6. So that's going to be 407 plus 127 plus 22. Let's just double check to be safe. 407 plus 127 plus 22 gives me 556. And that's my x squared values. So far I've set up the problem the way I want to set it up. And now we're going to start computing. So let's do the sum of squares first. And we're going to do sum of squares total. So SS total, SST, is going to be equal to the sum of x squared minus g squared over capital N. Capital N is the total sample size, so it's all the data points. And since we have 5 in each group, it's going to be 15. So sum of x squared we have here, 556. The grand total is 80 squared over 15. So that's going to give me 556 minus 80 squared over 15. So let's do that. That's 426.67. Let's take a look at that. 556 minus 426.67 gives me 129.33. And that's my sum of squares total. So that's easy enough. I'll put that in a box. We're going to need that later. So now we'll do sum of squares between. Now, you only need 2. So we know that sum of squares total equals sum of squares between plus sum of squares within. Right? So we know this. So all I need is 2 of the 3. The total I have. So I can either do the between or within. I don't have to do all of them. I just need 2. And if I do 2 correctly, then the other one is easy. I just subtract. Right? So I'll do all 3 for this example, but you only have to do 2 of the 3 to actually get all the information. Let's do sum of squares between. That is equal to total 1 squared over n1 plus total 2 squared over n2 plus total sub 3 squared over n3. Those are the numbers in each group, right? Let's make that a little nicer. That one came out a bit sloppy. These things are challenging too. Because you're not looking when you're writing on the screen here. I'm writing on a blank tablet. And it appears on the screen. So you're not actually looking at what you're writing. You're looking at what you're writing on the screen, but you're not looking at the tablet. So it's a bit of a hand-eye coordination issue when you do these things on a tablet. This is going to be also minus the g squared over n, which we already have. So that was 426.667, so that's easy to compute. Let's do this part first. T1 is 45, so 45 squared over 5 plus 25 squared over 5 plus 10 squared over 5 minus 426.67. So what does that give us? Obviously, I can't do that in my head, so I'm going to move it over here and do it. This gives us 405. That's not it again. 125 and 20. So 405 plus 125 plus 20. Minus 426.67. 405 and 125 is 530. That looks like it's 550. Let's double check. $550 minus 426.67. So what's that going to give us? $123.33, and that is your sum of squares between. So we've done total, we've done between, and we need to do within. Well, we don't have to actually do within. I can do total minus between. So 129.33 minus 123.33. Within is going to be 6, but I'll do it formula. I'll use the formula here, so to prove to you that it's 6. But you don't have to do it. If you've done these two parts correctly, you know that it's 129.33 minus this value. You get 6. But let's do it just for the sake of doing it. Maybe I want to zoom out a bit. Okay. So let's do sum of squares within. So this is equal to the sum of squares 1 plus the sum of squares 2 plus the sum of squares 3, which we need to compute here. So sum of squares 1 is going to be the sum of x sub 1 squared minus the sum of x sub 1 quantity squared over n sub 1. So I know that to be I gotta slide over here. Let's slide over and look at this. Actually, let me move this. Let's move this to another spot so I don't have to keep sliding back and forth here. I'll try to organize this better. Let's put it on the bottom here. So, sum of squares, whoops. Oh, I have that already. I'm just trying to organize here and failing. So sum of squares 1 is the sum of x sub 1 squared minus the sum of x sub 1 quantity squared over n1. So that gives me this value, 407, minus this value, 45, squared over n sub 1, which is 5. We did 45 squared over 5 here. I got 405. So this stuff is already here, right? So I don't have to do all these calculations again. So 405 is here. So this is 407 minus this value, which is 45 squared over 5, 405. And that gives me 2. Let's do sum of squares 2. That is sum of x sub 2 squared minus the sum of x sub 2 quantity squared over n sub 2. That gives me this value, 127, minus sum of x sub 2 squared over n sub 2. We have that here. 25 squared, we call it t, but it's really x sub 2. 25 squared over 5 is 125. So that gives me 2. And let's look at the third one. This is simply sum of x sub 3 squared minus sum of x sub 3 quantity squared over n sub 3. That gives me 22 here. 22 minus 10 squared over 5, which we have here is 20. So that's also 2. So we have sum of squares within is 2 plus 2 plus 2, as we thought, and we get 6. So 6 plus 123.33 gives you 129.33. And you're done. So you've done your sum of squares for between, within, and total. You partitioned the variance that way, and now we're ready for degrees of freedom and to finish the problem. So let's do degrees of freedom. Degrees of freedom total is n minus 1. So here it's 15 minus 1 is 14. Degrees of freedom between is n minus, sorry, made a mistake there. Let me erase that. Degrees of freedom between is k minus 1, where k is the number of groups. We have 3 groups. Minus 1 gives us 2. And the degrees of freedom within is n minus k. That's 15 minus 3 groups, which gives me 12. And as you can see, 12 plus 2 add up to 14. So I have my degrees of freedom. Now I need my mean squares. These are the average variances between and within. So that's sum of squares between over degrees of freedom between. Sum of squares between is 123.33. Degrees of freedom between is 2. So this is going to be a massive number. 61.67. Huge amount of variance between groups. That means the treatment is working, right? If this MSB is large, that means there's a huge amount of variance between the groups, and that generally means the treatment is having an effect. Mean squared within is the within groups variance, which we also call error, or I also call individual differences. So people in the same group are going to vary, and this is how much they vary due to just being different. They all get the same treatment, but they're just different human beings, so there's going to be some kind of variation. And that's sum of squares within over degrees of freedom within. Sum of squares within is 6. Degrees of freedom within is 12. So this is a very small number at 0.5. So then F is equal to the mean squared between over the mean squares within. And that's going to give me 61.67 divided by 0.5. $123.34. What a massive F value, right? So let's go back. Now that we got the F value, let's look at the problem again. State the null. That's easy enough. The null is ibuprofen, which is Advil. Has no effect on back pain. Basically, all the groups are going to be the same. It means the placebo group, the 200 milligram group, and the 400 milligram group will have no difference, right? And the alternative, H1, that looks like A. Let's make that look like an H. But that doesn't look much better. My drawing skills on this thing, and people use these tablets to actually draw, like artists drawing stuff on these tablets. So like, I don't know how in the world they do that. They must be a lot more talented than I am. My artistic abilities are massively limited, especially with regard to drawing and sketching. It's a complete disaster. The alternative is that ibuprofen has an effect. Remember that this is not directional, it's always non directional when it comes to the calculating the F ratio. So all we're saying is there's no difference or there's some difference. Now, we don't know where the difference is, so if I reject the null and I support the alternative, we then have to find which groups are different from each other. That's why we do the post hoc tests. So based on this huge value, which is, I mean, it's crazy. This F ratio is like just massive. 123.34 F ratio? I mean, that is just huge. I mean, that's so huge, I'm going to actually run it again to make sure that it's accurate. So let's do... I have it run here. Let's see. I'm just running it to check the validity. That's not what I want. So let's do analysis of variance. And I call this back pain. And then we have a dummy variable, which I coded already before this started. And it's, yeah, it's just massive here. And let's do summary of that. So when you do R and you run the analysis of variance like this, it spits out some of the information. You got to do summary to get all of it. And that's all of it. And the F value is 123.3 something. And that's what we got. So it is a really massive F ratio. And you see the probability being like really pathetically small. Because it's obviously a huge, huge effect, right? So we may want to run the Tukey tests here. Let's run it out of, I'm gonna have to call something a summary here. So summary back pain. So this is where the this is, can be annoying because you got to code this correctly, which is one of the reasons why I'm not teaching it to you in the lab, because it's going to go crazy if you make one little tiny error here, which I can do too. Okay. So I have summary back pain. And I gotta do this to look for Tukey. Oh, and it doesn't want me to do that. Okay. That's okay. I can do it this way too. Oh, doesn't want me to do it that way either. Okay. Well, we know that the groups are different. We'd have to run it this way, but this one is giving me fits because, so basically when you're dealing with R, what you're dealing with is something that is very inflexible. A fitted model object. So what I like to do is you look at the syntax. If you ever want to pick up R, you're going to look at the syntax here, and it's going to say summary of X, which is an object, which is the outcome of AOV. So when I do the analysis, AOV is the analysis of variance. So when I do the analysis of variance, like this, I have to save this as model. I have to save this as an object. So I'm going to call it model backpain. Save it as a variable, like this. And now I can do the Tukey thing with this object. That's got to be the exact type, and you can't make any mistakes. And there we go. So this is showing me that there's massive differences for all three here. The difference is -3 from 400 to 200. But I can just find the means of these columns anyway, right? There's a difference of 4 here between placebo and 200, and a difference of 4 between placebo and 400, right? And then the p-values are all tiny. This is E means times 10. So this is 5.98 times 10 to the negative fifth. 3.30 times 10 to the negative sixth. And this one is, the placebo to 400 one is so small, it's not even registering. That's how different it is. So they're all different from each other, right? Now the good thing about this problem is I'm not going to probably have you do the Tukey post hoc tests on the exam, because the exam is so long as it is. And so I kind of didn't want you to do the Tukey tests. And I showed you how to do it in class, but you know, I mean, it's good. You only do the Tukey tests, the post hoc tests, if you have a significant F. Now we have a huge significant F, and therefore these groups are so spread apart that they're all basically different from each other. Not surprising, right? But for the exam, I'm not going to probably ask you to do it. So remember, if the ANOVA is not significant, you do not do post hoc tests. And if you remember that for the exam, you're going to be in a good spot, right? It's going to make our life a lot easier. But basically, this is Tukey HSD is how I would do it in R. Let's go back. So we solved it. F is 123.34. We reject the null. I did the Tukey tests in R, and they were significant. So, yeah. That's the end of the problem, basically. That ibuprofen has an effect on back pain, and it's a pretty profound effect. So it's not even close. So, like, the type 1 error rate on this is, like, I mean, it's just ridiculously small. It's actually here. It's 0.000000009. That is our type 1 error rate for this problem. So the idea that we're making a type 1 error here is so infinitesimally small. And you'll see this when I do the critical F too. Here's the actual probability of type 1 error. It's 9.97 times 10 to the negative ninth, which is 0.000000009. I don't even know how I'd even say that number. It's just really pathetically small. So therefore, there's almost a 0% chance, almost zero chance we're making a type 1 error here. Which is great. If I want to look at the critical value, which I'm going to ask you to do, you're going to go to the table. So let's do that. Table for F. Now I ask you for 0.01, right? Let's see. 0.01. Doesn't matter because the F value is so large, 0.01 means nothing. Degrees of freedom numerator is k minus 1, k being the number of groups, so 3 minus 1 is 2. So 2 in the numerator. Denominator is n minus k. N is 15, K number of groups is 3, 15 minus 3 is 12, so I want 2 and 12. And I want the bold. The bold is 0.01. The regular font is 0.05. The bold is 6.93. So that's our critical value. Wow. Really scared of that critical value. I actually skipped the critical value part because the F ratio is so big. But the crit value of F is 6.93 from the table. Remember, this is always going to be positive. So 2 and 12, 6.93. It's positive. It's always positive for F. Right? So now, if I wanted to, for no reason whatsoever, I draw the F distribution. Remember, it's positively skewed distribution. This is 1. Right? That's the mode, right? 1. So when the null is true, it's going to be around, F is going to be around 1. Our crit F is here at like 6.93. And our actual value is just absolutely crazy. 123.34. So I'm like off the page here. So it's like somewhere over here. 123. So it's basically off of the damn whiteboard here. That's where our obtained value is. Since our obtained value is definitely in the tail, we reject the null. But with a huge F value, I don't even, unless I ask you for the critical value, which I actually do, like to reject the null, I see this big number, I'm like, yeah, I don't have to check. It's just ridiculous. So the between groups variance is just so much bigger than the within groups variance. The treatment is working great. Not that interesting, but you know, the treatment's working great. Reject the null, and you would do post hoc tests, and it would be Tukey tests, and they're all significant anyway. And we're not going to calculate them because you're not going to need them for the exam. So hopefully that helps you step by step how to do the one-way ANOVA, and I'll be back for stuff on regression soon. Bye for now.